This is the first of a series of videos about the derivative that all go with the handout entitled Intro to Derivative Notes. Let's start by looking at this example shown in the graph here. We have the graph entitled Moving Vehicle. On the x-axis we have time in hours, on the y-axis we have distance traveled in miles. How far did this vehicle travel in 5 hours? So if we look from here at time 0 to here, that's our 5-hour time span. So how far did it travel in 5 hours? If we look at the y-axis, you will see that at time 0 it looks like we're about at a distance of 25 miles from some starting place, from something, and at the end we end up at 100 miles an hour. So we start out basically at the point 0 hours 25 miles, and we end at 5 hours 100 miles. So how far did the vehicle travel during that 5 hours? It looks like it traveled 75 miles. What was the vehicle's average speed? Well, speed or velocity is distance divided by time, like miles per hour in this case. So it's 75 miles in 5 hours, so that's 15 miles per hour. Now, what algebraic quantity did you calculate in order to answer that question? And anytime I ask one of these questions, you can pause and see if you can answer it before I answer it. Well, if we look at the graph here, what we did is we looked at the change in the y value, and delta means change in y, divided by the change in x. And if you remember from algebra, that's the quantity slope. Slope, which is equal to change in y divided by change in x, in this case 75 miles over 5 hours. What does the fact that the graph is linear tell you about the vehicle's velocity? Well, it tells you that the velocity is constant. So we have a constant velocity in this situation. Now if we look at the next example is of a bird in flight. Now this bird in flight is clearly not going at a constant speed. This is not probably the best example in the world, but this bird, we're going to assume that before 1 second we haven't started timing. So for the first second the bird's basically sitting on the ground doing nothing. We have some negative values here, we'll just ignore those. So the bird's just sitting there, and then at 1 second after we start timing it takes off and it flies up in the air and it dips down and it flies back up again. And its height above the ground in feet is measured on the y-axis. So what I want to know is what's the average velocity, and I guess we can think of this as its average velocity up above the ground. It's how fast it's traveled vertically. So what's the average vertical velocity during the time shown on the graph? So I'm going to actually write vertical in here because that's really what I wanted to know. During the time shown on this graph. Well, in the time shown in this graph, since the bird hadn't actually started flying until 1 second, we're going to start at 1 second. So at 1 second, it's 0 feet off the ground. And at the end, at 7 seconds, we are at 30 feet off the ground. So the average velocity would just be the velocity of the line between these 2 points. So if we were just to imagine kind of straightening out, just saying if we just realized over that 6 second period from 1 second to 7 seconds to 6 seconds we traveled 30 feet total, we're just looking at 30 feet divided by 6 seconds. So 30 feet total divided by 6 seconds total gives us 5 feet per second as the average velocity. So the average velocity, basically we treat those 2 points as being on a line, as if it were constant velocity. Now I'm going to erase this because it's going to get kind of crowded with some of the other things I'm going to draw on it. What is the bird's average velocity during the first 2 seconds of its flight? So the first 2 seconds, we're starting at 1, 0, and we're ending up at 3 something. It looks like about, we're going to say this is 3 seconds, 26 feet. And here we're at 1 second, 0 feet. So once again, we can treat this as the slope of the line between those 2 points. We can say we went 26 feet in 2 seconds, or about 13 feet per second. Now, what's the bird's average velocity between 3 and 5 seconds? Well, between 3 and 5 seconds is about right here. So let's figure out where the bird was here. This is at the point 5 seconds, and it looks like about 20 feet. So the average velocity here, now notice as I go from 3 to 5 seconds, I want to actually look at my slope in terms of y2 minus y1 over x2 minus x1. So if I treat x1 as the point 1, 0, I'm sorry, let's just call that point number 1. x1, y1 is the point 1, 0, and the other one is x2, y2. So this would be x2, y2 over here. Then I would say y2 is 20 minus 0 divided by 5 minus 3. Oops. I totally did that wrong. Sorry. I'm trying to go from 3 to 5 seconds. So we'll call this one our x1, y1, and we'll call this one our x2, y2. So when I do slope is equal to y2 minus y1 over x2 minus x1, I'm saying 20 minus 26 over 5 minus 3. So this is negative 6 over 2, which is negative 3 feet per second. So this is a case where we have a negative velocity. And in physics, if you've had any physics, you'll recognize the velocity is a vector quantity. It means it has magnitude, its speed, and a direction. And in this case, when the bird is going downward, it's losing altitude, it has a negative velocity. So here we notice that we have a positive 13 feet per second and negative 3 feet per second. But if we went straight from the beginning to the end, it was overall a 5 feet per second. Now, what happens at the very peak? So what happens right at 3 seconds? So what's the bird's velocity at the peak? Well, if it's a positive velocity going up to the peak and a negative velocity going down, what's in between positive and negative? 0. Right at the peak. And you can actually imagine this. If you imagine throwing a ball up in the air and watching it come to the top and then turn around and come down. At the very top, there's an instantaneous pause where there is 0 velocity when it's changing direction. So it's actually 0 feet per second. So it changes from negative, or in this case, changes from positive to negative velocity. So it changes from positive velocity going up to negative velocity going down. Now, what's the bird's velocity precisely at 2 seconds? So this is a totally different question. We've been talking about average velocity, and an average velocity is always in between 2 points. What is the bird's velocity precisely at 2 seconds? This is a little more difficult question. So I'm going to draw a point that we're talking about, this point right here, precisely at 2 seconds. My problem with this is I don't have 2 points. And if I don't have 2 points, I can't use my slope formula because I need to be able to have a y2 and a y1 and an x2 and an x1. But all I have is the point 220, that at 2 seconds we're at 20 feet. So how do I figure out slope? To figure out the slope, which is the velocity, I have to have some sort of a line. So what kind of a line would I draw to estimate the slope? Well, I'd want to draw a line that has a slope similar to what the slope of the curve is at that point. If you want to stop the video and think for a minute what you think that line might look like, you can. But I'm going to turn it back on. Okay, welcome back. Maybe you never turned it off, but you're still here. The actual line that would give you the best slope, the slope that is the slope at that point is a tangent line. So I'm going to attempt to draw a tangent line. I don't think I drew that terribly well. I think I'm going to reattempt that. Let me get my skinny eraser here so I can get right in there. Okay. So I'm attempting to draw a line that just touches exactly at one point there. So I want to draw a tangent line to the graph. And if you recall from geometry, a tangent line just touches the graph at one point but doesn't cross it. So the tangent line touches but doesn't cross the graph at exactly one point. Okay, so the tangent line touches but doesn't cross the graph at exactly one point. So I would draw the line on, and then I'm going to estimate the slope. So if I look at this line, it looks like that this line goes through the point down here and up here. And to for the best guess that I have, this is a difference of 2 seconds in the x direction. In the y direction, we have a difference of 20 seconds. So it looks like my best guess here is that the slope is approximately 10. Let me write slope better. Looks like shope. Slope is approximately 10 feet per second, as I did 20 divided by 2. So to estimate, draw a tangent line and estimate the slope. Now, obviously we want to get this a little more precise. So let's take a look now at how we could be a little bit more precise with this. That'll be the focus of video number 2.